Hello everyone and welcome to part 3 of this week's lecture. In this lecture we are going to look at Archimedes' principle and Pascal's law. So let me just remind you what we have discussed so far. So we looked at hydrostatic pressure and how the hydrostatic pressure varies with the depth of the fluid. But if we look at a certain plane in this fluid at rest, we will see that the pressure at point here and point here and point here will be equal. So all the points on this plane would have equal pressure in all directions. So that is what we call the isotropy of pressure. Okay. So let's look at it that if we can mathematically prove this concept. So to do that, let's consider a wedge of a fluid. And in this wedge, we have different forces acting on it. So we have the F2 that is the horizontal force, we have F3 that is a vertical force, and then we have F1 that is a diagonal force. So we can write this force in the form of pressure times area. So we have F1 is equal to P1 times the area that is perpendicular to its direction. So we have AD, that is the area of this plane here. Then we have F2 that is P2 times BD, and BD is the area that is perpendicular to force F2. And then we have F3 that is P3 times CD. Okay. So we know that when a fluid is at rest, the net force on that fluid should be 0. So it means that the horizontal and vertical forces are equal. So we can write the vertical projection of force vector F1, that is F1 sine theta, should be equal to F2. And similarly for F1 cos theta, that is the horizontal projection of force vector F1, we can write F1 cos theta is equal to F3. Okay. And from trigonometry, we know that we can actually write sine theta also for a triangle as the vertical dimension over its diagonal dimension. So we can simplify this equation further for a horizontal plane that F1 that is can be write as P1 AD, and then we can write sine theta as B over A should be equal to P2 BD. And we can cancel out this BD term on both sides, so we have P1 is equal to P2. So for a vertical force, F1 cos theta should be equal to F3. And again, we can write this cos theta from trigonometry as C over A. So by putting values here for force P1, F1, we have P1 AD times C over A, and then we have P3 CD. So CD again will cancel out, and then we have P1 is equal to P3. And by chain rule, we can write P1 is equal to P2 and is equal to P3. Okay. So what it means that the pressure at a certain point or at a point in the fluid at rest acts equal in all directions. Okay. So over this plane, at any point, the pressure should be same. Okay. It will be different to pressure on a different plane, but as far as you are on one plane, it should be equal over this whole plane. Okay. So this is what also gives us the definition of Pascal's law. So Pascal's law observed this isotropy of pressure, and he came up with his law that states that for a confined body of fluid, so if you exert pressure on one end, the pressure will be transmitted to the whole body of fluid equally in all directions. Okay. And the very common example of this Pascal's law is a brake system that you have in your car, or hydraulic cranes, for example, and hydraulic, for example, jacks that you have in your garage. So let's look at it. So for example, you have this hydraulic pump here, and normally in this hydraulic pump you have two pistons, and one piston is narrower than the other one, and we will see in a moment why we have this kind of arrangement. And normally the car sits on the larger piston. okay? And you apply a force F1 on this small piston, and it generates a pressure of P1, and that transmitted through this fluid to this piston that experience a pressure of P2 or a force F2. So we can write these pressures from hydrostatics as P2, the pressure on point 2 or on piston 2, is equal to P1 plus rho g delta H. Okay, so that is what we saw in hydrostatic. And we know from isotropy of pressure that if these two pistons are at same plane or at same point, the pressures should be equal. So we can write P2 should be equal to P1. And if we express these pressures in the form of force, we can write F2 over A2 should be equal to F1 over A1. And we get an expression for the force F2 that is acting on the piston P2. Now, if we increase the area A2 much larger than A1, we will see that we get a similar effect in force. So it means that if A2 is larger than A1, then we have a F2 larger than F1. So for a confined liquid, the applied force can be amplified by varying the areas, okay? And we can increase this area or this force as much as we like by upscaling the area accordingly, okay? So that is the reason why we place this car on the larger piston, because by doing that we can actually amplify this small amount of force into a much larger force that can actually lift the car, okay? So that is what is the isotropy of pressure and Pascal law. Now let's look at another important principle, that is buoyancy, and fundamentally it's more physics than engineering, but actually it has a lot of significant applications in engineering as well. So let's look at it. So buoyancy is a force that is in the upward direction exerted by the fluid on any immersed object. So you all might have experienced buoyancy if you ever tried in a pool, for example, try to push a ball under the surface of water, and you might have experienced that there is a enormous force trying to push this ball out, and if you let this ball go, it just rockets out of the water. So this magical force is what we call buoyancy, and this buoyancy is nothing other than the net result of hydrostatic pressure distribution, okay? And that is, for example, I've shown here. So you have this ball, and that is submerged in water, and because of the hydrostatic pressure of water, you will have this pressure on the surface of this ball, and at the surface you have low pressure, while as you go down or move toward the depth of the pool, you see that the pressure increases, and that is why you have a net upward force acting on this ball. So we can calculate this buoyancy force by solving this integral here, and this integral is relatively easy to solve for a spherical or a cylindrical shape, but if we are talking of very complex shapes, this integral is also fairly difficult to solve. Lucky for us that we don't have to solve this integral, because we can use a shorthand method that was developed by Archimedes in centuries ago. And Archimedes was a Greek mathematician in 3rd century BC who came up with this idea. And there is a very funny story behind it, that he was taking a bath, and when he enters the bath, he notices that the water came out of the bath, and he felt some buoyancy force. And at that time, he came up with the idea that a buoyant force on an object is equal to the weight of the fluid displaced by the object. Okay, and so if there is an object, for example, here we take this example of a stone that is immersed in water. So this stone experiences two forces. One is called the weight of this object, and the second one is the buoyancy force. Okay, so just by doing a simple force balance, we can see that the net force on this object that is immersed in water should be equal to the weight minus the buoyancy force, that is Fb. So the weight of the solid is fairly easy to write, that is mg, and we can write m in the form of the density of the solid times the volume of the solid. And then we have the buoyancy force that is equal to the weight of the fluid displaced by the solid. Okay, so the weight of the fluid displaced by the solid, we can write it as rho L times G and V of the solid. So here we are using the V of the solid because that is the volume that will be replaced by this volume of the solid. Okay, so the net effect of this buoyancy and weight force will dictate if the object is going to swim or float. Okay, and all objects feel buoyancy. It is much more obvious when we are looking at a ball submerged in water, but all the objects on the surface of Earth experience buoyancy because they are in the atmosphere. So a mug of coffee sitting on the table is also experiencing buoyancy by the atmosphere that is equivalent to the weight of the fluid displaced by that mug of coffee. Okay. So the buoyancy force is normally much smaller for gases because the reason that the density of gases are much smaller compared to the densities of liquid. So the buoyancy force on a gas or by a gas would be 3 orders of magnitude lower than the buoyancy force that will be for the case of the liquid. Okay. So we can now let's look it in with a bit more sophisticated mathematics. So we can consider a cube that has a height h and has a volume v and is submerged in liquid. And at the bottom of this cube we have a pressure P2, and at the top we have a pressure acting that is P1. And let's look at the force that is exerted on this cube. So we have F that is equal to P2 times A minus P1 times A, that is the arbitrary area, and we can take the area out and we have this expression here. Also from hydrostatics we know that the pressure at this point P2 should be equal to sum of this pressure P1 plus the pressure due to the weight of the fluid, that is the hydrostatic pressure. So we can write the value of P2 in this equation as here. So we have F1 should be equal to rho F, that is the density of the fluid, times gravity times height of the of this arbitrary height of this control volume times the arbitrary area of this control volume. So we can replace this height times area in the form of the volume of this cube. So we have force is equal to rho F g times V, and we know that rho F times V should be equal to m, that is the mass of the fluid, times gravity. So we have the force acting on this object equal to the weight of the fluid. Okay, so we can write this weight of the object or this force in the form of buoyancy force, that is equal to density of the fluid times the gravity times the volume displaced of the fluid. And if we are looking at an object, for example, that is submerged in water, so there would be another force on this object that would be the weight of this object, that is the gravitational effect. So we have Fg is equal to mg, and we can write m as rho object times v of the solid times the gravity. Okay, so the net force on this object will be the balance of the buoyancy force and the weight force, and we can write the net force as Ft is equal to mg minus rho Fg times the displaced volume by the volume, the displaced volume of the liquid. And the net, the balance of these two forces dictates, as I said, if the object is going to float or sink. And this buoyancy force comes from the nothing but the hydrostatic pressure distribution effect. Let's look at this example and see if you got this buoyancy effect correctly. So we have, let's say, a weight that weighs around 7 pounds, and then you submerge this weight in a tank, and this weight displaces 4 pounds of water. So what would be the buoyant force on this object? So pause the video for a second and try to answer it. And if your answer is 4 pounds, you are correct, because although this weight weighs 7 pounds, but it only displaces 4 pounds of water. So the buoyancy force would be 4 pounds in force. And that's what the Archimedes principle explains, that the buoyant force is equal to the weight of the displaced water. Okay. And again, just to re-emphasize that the balance of these two forces, that is the buoyant force and the weight force, that determines if an object sinks or float. So if you have, for example, a heavy cube of steel that has a very large, for example, weight force but small buoyant force, it will sink because the net force is the downward. While if you have an ice cube that has a higher buoyant force compared to its weight force, it will float on the surface of the water. Okay, let's try this concept question to judge if you understood the concept of buoyancy correctly. So does the buoyancy affect the reading on your bathroom scale, or is this effect negligible? So another way of looking at this question is that if you weigh yourself in vacuum, would you weigh more or less compared to if you weigh yourself in atmosphere? So pause the video for a minute and try to answer this question. Okay. So if your answer is that you will weigh more in vacuum, you are correct. And the reason being that when you are in vacuum, there is no buoyancy effect because there are no molecules around you that are giving you this buoyancy effect. But when you are in the atmosphere, the air around you or the atmosphere around you is actually is causing the buoyancy effect and trying to lift your body up. Okay. So let's try to calculate this buoyancy effect. So let's say you have a volume of a typical human being that is 60 liters. It means that the amount of air that your body displaces is 60 liters, and in SI unit is 0.06 cubic meter. We know the density of air, we know the gravitational constant. So from this equation, we can calculate the buoyancy force, and it should be 0.07 kg or 0.16 pounds. It means that you will weigh 0.1% lower in atmosphere compared to if you weigh yourself in vacuum. So although this effect is negligible, it's not zero. And this effect becomes more important when we are talking about objects, for example, that are very light but very large volume objects. So you can think of, for example, that the buoyancy effect on this very light object will be much more significant, and then you have to correct for this buoyancy effect in terms of the weight of this object. Okay. So that's more or less all about Archimedes principle and Pascal's law. And in next lecture, we will talk about different devices that we can use to measure pressure. Okay. Thank you for your time.